Welcome to the revision of the bandsaw blade by the R&D department of the Flugenham Corporation. Meet the geniuses behind this product pitch. Mehul Mamadwar,
Kenton Tran,
and Kevin Fernandez.
Before we get into the revisions that we have made to the bandsaw blade, let's get into a little history about the bandsaw. It's been around since the 1970s and its primary function is to cut desired shapes from sheets of material. They have very recently been started to be replaced by laser cutters, which essentially perform the same function, but the machines are much costlier than the bandsaws. To better understand the applications of a bandsaw, let's take a look at a few visuals. Using bandsaws may require some skills. Now you can see a skilled laborer making an arc. One of the most basic applications will be to cut large chunks of wood into more usable pieces. Additionally, bandsaws also let you make smooth, straight, inline cuts. So what kind of material is used in a bandsaw blade currently? Most common ones are made of high quality, high carbon steel because of their weight or strength. Although they are harder to heat treat and costlier to manufacture. The material used in the blades greatly varies with the material that is getting cut and thickness of the material being cut. The bandsaw blades we are suggesting is for a very specific category of materials and a specific thickness. Hence our choices are different from the most commonly used industry standard ones. Heat treatment of the bandsaw blades varies with the material used to make the blade, although the manufacturing process is pretty standard and remains same for all kinds of materials. It is demonstrated further into this presentation.
The market that we are targeting is aluminium, brass, wood, plastic and steel because of their popularity. The thickness of the material to be cut is between 3/8 of an inch to 1 1/4 inches based on the industry standards for vertical bandsaws. The length of the bandsaw blade is 72 inches.
The following constraints were set up to help with the MPI calculations. Tooth pitch and width of the blade were based on the minimum thickness of the material to be cut. Length and thickness of the blade were based on the machine being considered in use. Max deflection was set at 1% to ensure smooth finish at all times. RPM was set based on the hardest material that the blade was going to cut, which was steel.
The render below is based off of the bandsaw blade that we have designed. The geometry of the blade was based off the requirements needed to cut our hardest target material, steel. The diagram below shows the geometry of the bandsaw blade. Some of these have been covered in a previous slide. H is equal to the gullet depth, which is 0.95 millimeters. This was determined by the formula 1.5 times the thickness of the blade. The rake and clearance angles are based off the optimal degrees angles for cutting steel. This is 12 degrees for the rake and 25 for the clearance. The width of the set is equal to the thickness of the blade, as it has a standard tooth set. Standard tooth set is used as a general purpose cutter. We're using this as we're cutting a wide range of materials and thickness.
This slide shows our constraints calculations. I will not bore you with the details. I will only explain what the formulas are used for. The formula on the left is used to determine the tangential stress experienced by each tooth, whereas the formula on the right is used to determine the minimum Young's modulus required for each tooth to experience a max deflection of 1%.
For the MPI calculation, the constraints is the length of the blade is fixed, and it must support a tensile force without failure. Objective, minimize the mass of the bandsaw blade. The free variable is cross-sectional area of the material. The formula on the left is the mass. The formula on the right is to determine yield strength. The formula in the middle is the MPI formula. It is minimizing mass while optimizing for yield strength.
The graph on the screen displays the materials that passed the stage 1 of the MPI test. That is the materials whose yield strength was greater than 142 megapascals, and as well as the materials who lied above the yield strength versus density line.
For this stage, we added cost and density limits. The maximum cost of the material was set at $5 per kilogram. The maximum density was set to that of carbide, as it is also one of the most commonly used materials in bandsaw blades. Young's modulus was calculated using the formula shown previously. The limit was set at a minimum of 116 gigapascals. As you can see, different variations of steel were the only materials that passed the 3 tests.
Thanks for that drum roll, Kenton. As you can see, ASI 1025 low carbon steel was chosen as our material for the bandsaw blade, as it is the cheapest type of low carbon steel available, which satisfied all our requirements.
This is a brief overview of how a bandsaw blade is made. It first enters the annealing process, allowing it to be soft enough to be machined. It then enters an inspection area where it is determined that there is no deformation that occurred to the blade during the annealing process. It is then put through a milling process that cuts each individual tooth. The teeth then are inspected again to make sure that they are cut correctly. They are then set. The set width is determined by how thick the slot they want to cut. And then finally enters the heat treatment process again.
Based on the material that was determined by the MPI analysis, we designed our own heat treatment process to process our. The heat treatment is divided into 4 basic steps. Step 1, normalization. Step 2, full annealing. Step 3, process annealing after cold working. Step 4, case hardening.
Normalization involves heating a metal to a temperature that is roughly equivalent to its hardening temperature. This process improves its mechanical properties and refines the grain size. An increase in hardness and strength of the steel is also noticed. For this steel, we use temperatures between 885 degrees Celsius and 927 degrees Celsius. Normally, this process is performed before air cooling, and it takes an hour for this process to complete. Full anneal comprises of heating steel to above the critical temperature and slow cooling, usually in the furnace. The temperature is raised to 50 degrees above the austenitic temperature. It is held at this temperature till all of the material transforms into austenite. It is then slowly cooled at a rate of about 20 degrees per hour. The crane structure has coarse pearlite with ferrite. For this steel, we use a temperature between 857 and 927 degrees Celsius, and it takes 6 to 8 hours to complete. The next 2 processes are executed post-machining. Process anneal is mainly suited for low-carbon steel. It is a heat treatment cycle that restores some of the ductility to a product being cold worked so it can be cold worked further without breaking. The material is heated up to a temperature just below the lower critical temperature of steel. For this steel, we use a temperature between 593 degrees and 663 degrees Celsius. Case hardening is also referred to as carburizing. It is a heat treatment process that produces a surface resistant to wear while maintaining toughness and strength of the core. It increases strength and wear resistance by diffusing carbon into the surface of the steel, creating a case while retaining a substantially lesser hardness in the core. For this steel, we use a temperature between 843 and 885 degrees Celsius. It takes roughly half an hour.
Thank you for watching our pitch. We chose a personalization approach while designing this blade. Increasing the carbon content of steel just makes the steel harder to manufacture and increases its cost, as mentioned earlier. Just like cars, not everyone needs a car with 1000 horsepower. For some people, 125 horsepower is more than enough. Hence, by the same logic, not every customer needs a high quality blade. For people who just want to carve some wood, a blade with low carbon content is just good enough. Therefore, by customizing the quality of our blades to people's uses can help save costs for people who do not need high performance blades. This method can help increase our profits and turn the fortunes of our company around. Are you ready to ignite your brilliance? And finally, have a Merry Christmas and Happy New Year!